Hello, everyone. My name is Mahesh Anand. I'm a professor of planetary science and exploration at the Open University. I'm also the lead for the Living on the Moon exhibit that you have come across, and you can see the sticker. If you were actually coming in person, you would be actually receiving a sticker for our exhibit. My particular area of expertise is samples, so I work on moon rocks, all sorts of moon rocks, those that were brought back by Apollo astronauts, some brought by the lunar missions, and some that are present as lunar meteorites. But I'm interested in every aspect of the moon. And I also look after a big community of lunar science in the UK under the umbrella of NASA Solar System Exploration Virtual Research Institute. So I'm really excited to answer your questions that you may have about the moon and in general, anything to do with the space. And I look forward to interacting with you.
Hi everyone, my name is Hannah Sargent and I'm a planetary scientist at the Open University. So I'm particularly interested in resources on the moon, in particular water. So how can we find water? How can we make water? Because it is one of the most critical resources that we can use to make rocket propellant and to support humans for long duration missions. And I'm currently working on the LoveMe-X rover, which is hopefully going to be digging for water ice in the polar regions of the moon.
Hi, my name's Sam Faircloth. I'm a postdoctoral researcher at the Open University. Now, I have the exciting job of studying rocks that were brought back by the astronauts during the Apollo missions of the late 1960s and early 1970s. So the rocks that the astronauts brought back, we have quite a few in our laboratory at the Open University. And I, with the machines that we have there, measure particular chemistry, elements and isotopes within those rocks. And the reason I do that is to try and find out more about how the Earth and Moon formed, and also how the moon evolved, and therefore how did all of our planets and inner solar system bodies evolve.
Hi, my name's Neil Bowles. I work at the University of Oxford in the UK, and I work on studying the moon from the surface and also from orbit by sending spacecraft there. And I've worked on lots of missions, in particular NASA's Lunar Reconnaissance Orbiter and hopefully a new mission called Lunar Trailblazer.
Why don't we just get started, Hannah? It's a kind of an esoteric question, who will live on the moon? And in some ways, what we tried to do last year when we were at the exhibition is that most of the people came in and they thought that the title was Living on the Moon. So that meant that we were talking about thousands or hundreds of thousands of people settling on the moon, which is exactly the opposite of why we called it Living on the Moon, because it was more to do with humanity actually having the presence elsewhere in the solar system other than the Earth, in that context, rather than actually, starting a new colony on the moon. So Hannah, if you take it away.
So initially, the first people who are going to go to the moon are going to be your astronauts, your pilots, your scientists. They're the first people who really, who will be the explorers, just like the Antarctic bases at the moment, which are full of scientists doing really critical research there. But then it will move into some more engineering roles, perhaps the mining industry, because we want to access some of the resources on the moon to help us to survive there for longer periods of time. Perhaps even the construction industry might be able to lend some skills there to help us develop the infrastructure to support a long-term human base on the moon.
Great, that was excellent, Hannah. And I wondered if I can bring in Sam here. Sam, there is a question here which talks about, do you think a lunar base is necessary for further advancement in space exploration?
Yeah, I think it is definitely necessary to have some sort of base on the moon to further our understanding of what happens in space. And that's for two reasons. The first reason is that the Earth has this wonderful atmosphere around it, which means that we can breathe because it contains oxygen. But in terms of astronomy, it's quite difficult to see through this atmosphere into space. So if we've got a presence on the moon, we lose that atmosphere because there isn't really an atmosphere on the moon. And we can then see beyond out into the wider galaxy and the universe. The second reason is that if we've got a moon base on the moon with people there, we've then got the ability to get to other planets, so Mars, much more efficiently, much more quickly, and hopefully using less rocket fuel because we won't be going straight from Earth. But there is a caveat though. I think if we are going to have a base on the moon, we need to do it very, very carefully and responsibly and learn from some of the mistakes we've made on Earth and apply those to the moon.
Right, that's really a very sensible thought there, for sure, that we need to explore in a responsible and sustainable manner. And Neil, I wondered what you felt about this question, which talks about terraforming Mars. And the question asks, how can we terraform Mars, Earth's moon, or Europa?
Ooh, well, there is an important question which follows on actually from Samantha's comment. Should we, which is a whole other area, versus could we? Now, Mars is out of those three are really the only ones that you could terraform in the sense to make it like Earth, i.e. human beings could walk around on the surface eventually. You'd have to do an awful lot of work. It would take an awful lot of time, and you'd probably wonder if it was actually worth the effort in the end, because you have to do a lot to thicken up the atmosphere and add lots of carbon dioxide into it to get the surface temperature up and to get the water, so you can have liquid water on the surface and things like that. The moon or Europa is very difficult because they are much, much smaller than the Earth or Mars, so they have much lower gravity, so they don't retain an atmosphere for very long. And it's an atmosphere that you need to get anything else going. Now, that doesn't mean, of course, that you couldn't live underground in those places. So in theory, you could use the natural structures on something like the moon, say some of the lava tubes that might be present. We see evidence of little holes on the surface, essentially, which on Earth would mean there was a load of subterranean lava channels, which have formed when the moon was in more of its more volcanically active phases. And you could use those, essentially seal them off at the ends and turn those into kind of habitats. And then you could use the sort of techniques that people like Hannah have been developing to generate water or oxygen or other things like that, actually on the moon, to do that. So that would certainly be possible, but actually forming an atmosphere around the moon to then live on it, that would be quite difficult for any sustainable period of time. Europa is more complicated again. You'd certainly have to live underground on Europa if you were going to live on Europa, because it's right close to Jupiter, and Jupiter's got some really, biggest planet in the solar system, it's got some really nasty radiation belts. It's got very big magnetic field, traps lots of charged particles from the sun and from other places, and that gets really kind of nasty to live in. You can get kind of cooked from the inside out, if you like, by being too close to Jupiter. But you'd have to live inside on Europa.
That's great. Yeah. Some of these questions are quite difficult to answer because the complexity and the technological advancement that is needed to even get close to it is, it's so far from today but it's worth contemplating that one day this might be possible. And I wonder, in the same vein, we have another question here which talks about, let's imagine. Well, nobody can stop us from imagining. So let's imagine a situation where a section of humanity has already settled on the moon for several generations. So here we are talking about, a period of maybe 50 years, maybe 100 years. So we are looking over the next few centuries, perhaps. The question asks, will their anatomy and physiology be different from those living on Earth? I think a short answer to this is going to be almost certainly yes. And we already have some evidence for this because we have the International Space Station, which is going around the Earth for the past 20 years. And astronauts have been spending, quite considerable amount of time in one trip, as long as sometimes over several months, 6 months, or even longer. And there has been a lot of experiments going on to actually find out what changes have been taking place in their bodies, in their anatomy, etc. So I think there is already a serious amount of work that suggests that there are some changes that takes place when the human body is exposed to the environment in space. And you are going to face similar situation when you go to moon or you go to other bodies that have different gravitational field than the Earth. So we know there will be some changes, but exactly what those changes will be are difficult to predict. And that's where we need to continue doing experiments such as using the International Space Station and perhaps Moon in the very near future.
Question from a little one that might be quite nice to answer. So age 9, Austin, age 9, and this it kind of links to one of the questions you've already answered, but he asks, will I go to space in my lifetime?
This is really the part that I love. This is where if I was present in front of this kid, I would first put a moon rock in their hand and then make them so excited that afterwards they will be spellbound. Austin asks a very good question, and I would say that Austin is probably in the luckiest generation, which is most likely to go into space. And if you have seen the recent launches that have taken place, they are actually giving us a lot of comfort that we are getting ever so closer of returning humans to the moon. And again, NASA has actually announced that they are going to land the first woman and the next man at the moon by 2024. That's only 3 years from today. Yeah, a max 4 years. So Austin, you are only 9 years old, and in 2024 you will still be 13. And I would like to think that you have another 20 years to actually make multiple trips into space. So good luck to you.
Yeah, that's awesome. I think he's going to be really excited to hear your answer.
Excellent. Thank you very much.
No, thank you so much for your time at the end of a Friday. Much appreciated.
Hi everyone, we're the Gaia team at the University of Cambridge, and we're here to answer questions for you today on space and the Gaia mission. So looking forward to chatting with you.
One of my favourites. So could you collect some of Jupiter in a jar as it's made of gas from Dare in Dublin?
Well, that's a great question. And in theory, yes. But in practice, it's a bit harder because when we send a probe into the atmosphere, the drag in the atmosphere causes the probe to lose energy. So it's very hard to actually bring it back out. So you'd need a lot of fuel and very powerful thrusters to be able to return the specimen. And in fact, because Jupiter is a lot more massive than the Earth, the escape speed that you need to reach is also much higher than that you need on Earth. So it makes much more sense to actually have instruments on the probe that can do the measurements in the atmosphere.
Okay, so the next question is from Vasu in Chennai. How are scientists predicting and measuring all the stars and galaxies and Milky Ways?
So astronomers observe stars and galaxies in many different ways with many different types of telescopes, and that provides a wide range of information. For example, data collected by the European Space Agency's Gaia satellite allows astronomers to measure stellar distances and velocities, as well as properties of their spectra. All of this information is used to build models of stars and galaxies, and with those models, further predictions can be made on how these objects are formed, evolve with time and end. That is the very brief answer. The long answer is a whole study in astronomy.
Brilliant, thank you. Great, so the next question is from Chris in Greece. Will we ever be able to build a Dyson sphere?
Okay, right. So a Dyson sphere is an idea, a concept. It doesn't exist. For a super advanced civilization to build a gigantic shade around an entire sun to soak up all of the energy coming out of that sun and convert it to energy that the civilization could then use. Now, there's a lot of this energy. So today on the Earth, the sun puts about 1 kilowatt on every square meter every day. Now, that's like a full radiant heater burning down on us. So if you could imagine something the size of the Earth's orbit filled with detectors and collectors, then you'd have a huge amount of energy available to do something with. There are a few basic problems with this. The first is it couldn't be solid because it would be unstable and would just fall apart. And second, asteroids and comets and things like that would keep smashing it to pieces. So it would have to be just a huge number of spacecraft individually flying and clever ones to dodge the asteroids, and then collecting the energy and then somehow or other feeding it back to the Earth. So there could be an enormous amount of energy. In fact, I have a Dyson Sphere I ran up earlier. So here it is. So here's a sun, a little yellow sun. And here's a Dyson Sphere. So you can pop the sun in the Dyson Sphere, turn around and ping, there's your Dyson Sphere. The sun's in there, and this is soaking up all of the energy of that complete sun. So then the challenge and the interesting bit is to say, well, somehow you've got to turn that sunlight into energy that you can use. And of course, energy, once you've used it, turns back into heat. And so you've still got to radiate away all the heat of the sun somehow or other, which is not simple engineering. But more fundamentally, so all this is way beyond current technologies, but more fundamentally, it's hard to imagine a society that was so engineeringly inept that it needed all that energy and still had the capability to collect it. You'd think that a society that had a smart enough engineering that they could build a Dyson Sphere would actually be smart enough to build efficient machines, and so didn't need it.
So I think it's also really nice that instead of, so you can have a Dyson Sphere as a single entity, but there are also concepts now which think about, they are called Dyson swarms or Dyson bubbles. The simplest one of those is a Dyson ring, which is actually much like, let's call it a Starlink, so an interlinked entity consisting of different spacecraft, which would obviously not be covering the whole surface of the star, but just a smaller piece of it, which might be technologically more possible in the, well, not in the near future, but maybe at some point.
Perfect, thank you. Great, so the next question is from Laura in Massachusetts. What is space weather?
So with space weather concerns the conditions that happen just in the outer layers of our atmosphere, or outside of our atmosphere, where the sun is continually emitting a stream of charged particles. And these particles, just like a wind on Earth, they can push against things. For example, they can push against satellites, which means that the satellites have to correct their orbits for these forces. These particles, they can also push against our magnetosphere, so the magnetic field around the Earth. And so one very famous example of space weather is that when you have a solar flare, which you could call a space storm, the sun produces a large amount, a very strong wind. And so you can see this in the charged particles lighting up the night sky in what we call the northern lights or aurora borealis.
Well, that, if you don't mind my suggesting, that your number 6, the Milky Way Andromeda collision, this is something people ask all the time.
Yeah.
I remember being phoned up at an observatory in the middle of the night once by an insurance broker asking me exactly that question after a story about the future of the solar system, and should he do something about it? So the Milky Way and Andromeda are on a collision course. This, however, has 2 special aspects to it. First, it's going to be a long time in the future, about 4 billion years before the 2 actually overlap enough to be called a real collision. And on that same timescale, our sun will have come to the end of its life. And so what's happening in the bigger picture is going to be sort of irrelevant, because the Earth is going to be burnt to a cinder, and that will be the end of our solar system as we know it. But more generally, when galaxies collide, they do pull each other apart and throw stuff around, but only through tides, not through physical collisions. It's easy to forget that space is a big place and the distances between things are very large. And so even when you put 2 galaxies in the same place by colliding them, the number of physical collisions of stars is basically 0. The gas clouds, which are huge, will actually collide with each other, and they'll create new stars when they do it. But the individual stars will just get whizzed around a bit faster than they are now, and otherwise won't notice anything's happening, except the night sky suddenly got a lot more interesting.
Thinking what I can add to that.
Right, talk about the nucleus, black holes, what's going to happen to them?
Okay. So when these galaxies eventually collide through frictional forces, the supermassive black holes, which are in which are found in the centers of almost all galaxies, they will start to, let's say, sink toward the center of this newly formed galaxy. And there they will be doing a lot of funky stuff, including, so there are a lot of stars in the center of those galaxies. And because these black holes are perturbing each other's orbits, also the stars will be thrown into very chaotic orbits. And some of them, they will pass so close to the black hole that they will actually be completely destroyed. I think we don't have to worry so much about it because we are nicely on the outskirts of our galaxy, but planets more towards the center may also be impacted by this interaction.
Wow, I'm glad we answered that. That's super interesting and quite scary for a Friday afternoon. We wish you a fantastic weekend.
Hello, we're the A Message from Afar team, and we're curious about your questions on searching for extraterrestrial intelligence.
So Diego from San Pedro wants to know, could humans be the only intelligent species in the universe?
Are humans the only intelligent species in the universe? No, they're not, because humans are not the only intelligent species on planet Earth. The ability to use language to communicate does not distinguish us from other animals. When we search for extraterrestrial intelligence, we're not searching for humans. Whether life exists beyond Earth, we don't know.
Okay, Diego from San Pedro, again, would like to know, what would we do if we find another intelligent species?
Well, Diego, a great question, of course. This is one we're trying to prepare for, and we have many sort of aspects of it that we're pulling together to create some sort of framework and protocols to be able to do this. So we would announce a discovery after some period of verification to everybody in the world. It wouldn't be kept a secret. I think that's the first thing to mention. After that, if a message has been received or intercepted, then we've got to start to look at what we can find out about that. So we'll be analysing the signal that will start to commence with timely feedback to the public, of course. This wouldn't happen all in one shot. We would have to actually take this bite-wise and start to analyse it, different aspects of what the signal is. And we would get information and glean aspects of it from that to be able to tell everybody what we know. This would involve employing what we know about communication, all the different languages, 6,000 of them we've actually used, humans, over all the period of time that we've been using language on this planet. So they're great sort of templates for us to look into and compare. What do we know that's common amongst all those languages that can underpin our knowledge of what communication is and how it acts? The aspect of knowing what our brain does to actually constrain what language, how it operates, and that can actually give us a window when we know as much as we need to know on the communication of the alien civilization, the intelligence that we've intercepted. How intelligent are they? We'd be able to find out something about that from their communication. We'd also discuss the possibility of reciprocating that communication, but that is a big question that we have continually debate upon, and what is our policy and what information have we got from their communication that may inform us upon that. And we would involve a multidisciplinary team of all the experts that will be involved in some post-detection analysis, everything from theology through to law, obviously linguistics and communication, AI type areas, to social impact strategies to be able to get our message across in the best possible way to everybody.
Great, thanks, John. Srinjoy from Kolkata would like to know, we've recently seen a report which tells us that there are about 36 contactable alien civilizations within our own galaxy. How far is the nearest civilization from the Earth?
That,
sorry?
oh, go on, sorry. Okay. Go for it, Martin.
How far is the nearest civilization from Earth? Well, we fundamentally neither know the necessary nor the sufficient conditions for life to emerge. And thereby any attempt to attach some probability is pretty much speculation. Any prediction on the number of extraterrestrial civilizations that has been made is based on some assumptions, but which we don't know whether those hold or not, which essentially makes any number as good as any other one. If we happen not to be alone, the key question is how far away our closest neighbors are. But unless we understand how physics and chemistry turn into biology, our only opportunity to find out is to search.
I'd say that our nearest star away from our own sun is about 4.5 light years away, if I get it correct. And so that's the nearest possibility of a planet orbiting that sun. But then again, the Milky Way is vast. We're talking about something like 1,000 light years thick and roughly speaking 150,000 light years in diameter. So you can imagine the amount of distance and time involved in that, and the billions of possible planets out there. So with that in mind, where it might be could be on our doorstep or so far away that it would take generations to communicate with.
Brilliant, thank you. So Laura from Haverhill, Massachusetts would like to know, what do we know about extraterrestrial intelligence?
Right, what do we know? Well, we'd have to piece things together a bit like a jigsaw, in the sense that it could be anything. It could be like us, or it could be so different to us that it's so exotic that we really have not got a handle on it. But I would say it was subject to the same physical laws as us. That stands, as far as we know it, as a truth. That the home planet they're on, the environment, the proximity to its sun, will have some sort of physical impact on the way they are as a being. Their physicality, their size, this sort of thing. But the information exchange, the communication is key to any intelligent species being able to exchange information from generation to generation, from place to place. Like us, and what we're doing now, we're communicating with people potentially all over the globe, from our bedroom or wherever. And they would be wanting to do similar things to be able to extend their capabilities, to exchange knowledge so the next generation know that everybody in that generation can share information, and it optimizes their survival potential is one of the key things for any species. And that this technology, they would need to employ some sort of way of transmitting it, like radio. So these sort of things we can try to search for, we can try to anticipate and build some sort of profile of, given all these different variables. That's what we know.
Great. No, that's brilliant. Thank you very much. So we have a little bit more time left, and we have a really nice question from Carluke High School. What inspired you both, so it'd be great to get an answer from you both, to get into the field that you're in?
Okay, I'll start. From my point of view, I was studying artificial intelligence as a degree subject at university. And as I was progressing through that degree, I got interested in language and the aspect of AI, which is the linguistics, and being able to get a computer to be able to understand and communicate themselves. And at that point, I wondered, what is language? What makes it special, if you like, in the signal universe, of all the different possibilities, rather than just a noise, there's structure in there. And then I used the sort of blue sky, or even black sky in this case, because it's out there in space, possibility of the thought experiment. If we received a communication from another intelligence out there, how will we know its language? So that suddenly inspired me to look into it, look into all what our languages are comprised of, and then see if I could model and glean what we may be able to do if we received a signal from outer space. And that was even without thinking or knowing anything about SETI. It was SETI contacted me after writing this paper at the end of my degree that sparked everything off, and everything just went from there. It's become a passion and something that I want to do forevermore.
Thanks, John. Right, Martin, what inspired you?
I never wanted to do something that lots of other people do. So, you know, I started with some question, then came up with another one, and it was never a straight line. It was just, you know, changing directions all the time.
Perfect. Thank you so much. And thank you both so much for your time this morning and giving such fantastic answers to the questions.
Glad to be with you.
Hi, we are Galaxy Makers from Durham University.
We're here to answer your questions on space.
Okay, all right. Okay, so what happens when you fall into a black hole? Well, the answer is actually quite surprising. And in reality, if you are unlucky enough to fall into a black hole, at first nothing really happens. You don't even notice that you've fallen into a black hole. Unlike somebody who's watching you fall, they get very, very shocked because they don't see you fall either, but time for them slows down. So an external observer will never see you fall into the black hole. But you fall, and at first it's nothing. You cross the event horizon, as it's called, which is the edge of the black hole. But soon you begin to accelerate. And after a while, you realize that your feet are accelerating faster than your head if you're falling feet first. And so what happens is you get stretched in a process that I think it may have been Stephen Hawking called spaghettification, where you essentially turn into spaghetti because your feet are being pulled harder than your head. Now, of course, very soon you will disintegrate into little strings of spaghetti. But what happens to the remains of you? Well, you just keep falling. And then, interestingly, it all depends on whether the black hole is spinning or not. If the black hole is not spinning, then you hit something really, really nasty in the center of a black hole called a singularity. And that really is the ultimate fate that would happen if you fall into a non-spinning black hole. And it's not pleasant, I am sure. However, if the black hole is spinning, then you can go through the middle of the black hole because the singularity, you can avoid the singularity. In a spinning black hole, the singularity is a circle. You can go through the middle of it, and where you come out is anybody's guess. So the lesson is, if you see a black hole, avoid it. Try not to fall into it because it will not be pleasant. It'll be interesting for a few seconds, very unpleasant after that.
That was great. Thanks, Carlos. I'll definitely take fall into a black hole off my bucket list then. Brilliant. So the next question we have is from Diego in San Pedro Sula. And he asks, how many black holes could be near us?
Okay, so this is a really interesting question, and there's kind of different ways to answer it. So in terms of just ones that we actually know about, black holes close to us, the closest known black hole to the Earth is a black hole about 1,000 light years away. And we know about it. We can't see the black hole itself, but there are two stars that orbit that black hole. And given the orbits of the stars, you can work out how heavy is the object they're orbiting around that we can't see. And given its mass, it's about 5 times the mass of the sun. We suspect it's a black hole, combined with the fact that it doesn't emit any light. But given that black holes don't emit any light, the only ones we can see are those ones that are interacting with other things that are visible and are emitting light. But if we wanted to say, have a guess at how many black holes might be near to us, well, we could look at the distribution of local stars. And locally, there's about 5% of the mass of the sun per cubic light year in stars near to the sun. And given how stars form, they form in all different masses. And if you look at for every star you form that's, say, the mass of the sun, you're very unlikely to form a star massive enough to form a black hole. And it's stars above 30 times the mass of the sun that eventually will form a black hole. And so if we just look at how many stars do I have to form to produce one star massive enough to become a black hole, it's of order a few thousand. And when you kind of fold that in, that only 1 in, say, 3,000 stars will end up being a black hole, and the number of stars there are locally, you find that local to the sun, there's about a black hole every kind of 80 light year cube. So if I have a cube of space around the sun and it's 80 light years on a side, then on average, I'd expect maybe 1 black hole in that box. And so that's the kind of average separation between black holes close to the sun. But most of these we can't see. And yeah, we have to go much further until we find the first black hole we actually have evidence for directly.
What if there's a mini black hole? There could be many of those.
Well, of course, so this is all assuming that the only formation mechanism for black holes is the end of a star's life. If you have primordial black holes and they're the dark matter or whatever, then who knows, all bets are off, I guess.
There are a number of objects inside our solar system that are further away than Pluto. We'd call those dwarf planets. And these seem to have a very weird orbit that does not seem to be explained by the sun and the planets that we know. So it has been hypothesized that there is an extra 9th planet in the solar system. But what it could also be is something we call a primordial black hole. If that is the case, this black hole is about 5 times the mass of the Earth and is about the size of a tennis ball, just lurking in our solar system, which is a little bit scary.
Just a little bit.
The reason they're called primordial is because they were formed during the Big Bang. They were formed by a mechanism that's not understood, and they could be any amount of mass from a few grams to a few times the mass of the Earth. But the one that Anna is talking about would be at the massive end of things and could explain some of these very strange motions of some of the outer planets in the solar system. You think there is such a thing, Anna? Would you bet there is one of them?
A primordial, well, it seems that this scenario in which there is a 9th planet in the solar system is just as likely as a primordial black hole being captured, provided those things exist. Then it is a possibility.
I wouldn't say it's likely, right? So even the community is divided. Nobody knows if primordial black holes exist. As far as I know, they don't exist. So it's more likely to have another planet. I know planets exist.
Yeah.
So I wouldn't say it's likely to have a black hole at the edge of the solar system. It's completely the opposite for me.
Yeah. If we knew primordial black holes exist, then it's just about 50-50. Yeah. So I think it's highly unlikely, but a bit of fun.
That's for the next generation of scientists to figure out. Do primordial black holes exist or not?
These are tiddlers that you're talking about so far. And they wonder about the supermassive black hole at the center of the galaxy, which is much bigger than the ones you've been talking about. So this is one you can actually go back and look at the stars moving around at the center of the galaxy and see them moving in very short timescales. And then, as Andrew said for his answer, then you can figure out what is the mass that you need to make those stars move that quickly. And you come up with something that's the density of a black hole and many times more massive than these other black holes.
Brilliant. Okay, so the next question is from Vasu in Chennai, and they ask, how are black holes created?
Yeah, so let me just get going. So to introduce this in. So how are black holes formed? Well, there's many ways to end up life as a black hole. The traditional way in which physicists think black holes are made is through the implosion of a very massive star. So if a star gets too big for its own good, if it weighs more than about 30 or 50 times the mass of the sun, then eventually when these stars run out of nuclear fuel, which is what keeps them shining, but of course it's nuclear fuel, so it's eventually exhausted. So when the nuclear fuel in the center is exhausted, then the pressure that was keeping the star in place vanishes, because that was due to the nuclear powerhouse in the center, and the star just implodes, and nothing stops it until eventually it turns into a black hole. So that is the traditional way in which physicists think of black holes. But there are many other more exotic ways to make black holes. One of them would be in the very early universe, during the Big Bang, when small irregularities could also collapse under the force of gravity and become black holes. Those black holes could be extremely interesting because unlike the ones that form from stars that typically have masses comparable to the mass of the sun, the primordial ones could be anything from a few grams to very, very large. Then there's another way to make black holes, which are, again, possibly, well, not very well understood, but it turns out that every galaxy that we know of in the universe has something called a supermassive black hole in the center. So these are not like the traditional black holes. They don't weigh the mass of the sun. They can weigh anything between 1 million and 1 billion times the mass of the sun. Now these black holes maybe start life in some way, possibly as a stellar black hole, and then they grow. As galaxies evolve, then the mass falls into the black hole, and it can get bigger and bigger and bigger and bigger. So these are just some of the mechanisms in which black holes can form. No doubt there are others as well.
I think content-wise, I think given you just described how stars implode to form black holes, before going on to like exotic scenarios that may or may not have happened, I think the fact that the other black holes we know about are just the same stars that were slightly less massive, end up being held up by neutron degeneracy pressure, form a neutron star, and then if that neutron star accretes material later on to become more massive, or merges with another neutron star, then that object will become a black hole. And particularly given that's something we've just seen recently with LIGO, where we've seen a binary neutron star merger emitting gravitational waves, as well as a flash of light. This is like another interesting formation mechanism for black holes that we now know exists.
And perhaps the most exotic, but within reach way of making a black hole is to make it in a laboratory, in a particle accelerator. When the Large Hadron Collider in CERN was going to be turned on, there was a little bit of a fear that when these beams of fast-moving particles collide, that perhaps they could make a black hole in a laboratory, a tiny, tiny black hole of very, very, very small mass, but it could have devastating consequences because it could eat everything up around it. Luckily, the Large Hadron Collider was turned on and we're still here. So black holes were not formed, but in principle, it's not beyond the reach of human ingenuity to be able to figure out a way to make black holes in a particle accelerator, and then they need to figure out how to protect themselves from the huge gravitational power, the sucking power that black holes have. But we leave that for future generations.
Is this a worry for the collider that they're talking about that's coming after the LHC then, Carlos, do you think?
You mean the next particle accelerator is going to be 10 times more powerful than the Large Hadron Collider?
Yeah.
That could be a worry as well. Yes. I mean, it'd be quite fun to be able to make black holes in the laboratory and maybe experiment with them. You have to be very careful how you approach them because they are relentless. They are absolutely ruthless. Get close to one of them and you don't live to tell the tale.
Brilliant. You become spaghetti. I'm learning so much for a Friday morning.
Just the scientific term.
I really enjoy that. Science is great in so many ways. We got one really good question in yesterday, and it's a bit of a more generic question than the others we've had, but it's from a 6-year-old, so we thought it might be a quite nice one to answer. And this is from Evie, age 6, and she asks, what is space?
So Ali is not a 6-year-old, but so Ali knows how to talk to kids.
Well, not really. Not that the fundamental questions. What is space? I even don't know what is space. I don't even understand that.
Yep, that was it. She's asking the tough questions.
Yeah, I mean, I guess there are like local definitions, as in how, you know, if you're sat on Earth, how far upwards do you have to travel until you're in space? And that there's nothing that fundamental about the answer to that question. It's like a matter of definition. And in fact, I think recently I'm sure some people recently got their like astronaut wings who were like doing test flights in the 60s for the US military or something, because some redefinition of the boundary of space meant that some aircraft just counted as a spacecraft.
Oh, right. So the question is not the philosophical essential question. So I think what
the question, I assume the question is whatever we want it to be.
Right. But I think it's to do with what's space, what is beyond the Earth. I think that's what the question is.
Well, I was trying to cheat and answer the easy question. Space, according to so-and-so, is 100 kilometers up, or 50 miles, or this or that. But what actually happened? What are you in when you go there? Well, good question.
No, she's not asking what the space is made of. No, she's asking what is a space. It's a philosophical question to me.
Yeah, but I think she's not thinking about the philosophical language. She just heard about space exploration, and so what is space, right?
Well, it could be genius, right? 6 years old genius.
You have to know the answer, though, don't we? We are the space experts, and we don't know what it is we're talking about.
Right. I mean, I would say, space is whatever it is we move in, right? So we move in space, and here in our home, space seems to have 3 different directions. You can go lengthwise, widthwise, or in height. So that's space. It's where we move. But space is also out there, outside the Earth. There is a huge amount of space, and in fact, most of it is completely empty. As it happens, the stars that we see, even though when we look at the night sky, if you're lucky in the dark side, you can see many, many, many stars. In reality, those stars are very, very far away, and most of the space in between them is just completely empty. So space is whatever there is in our room, and it extends all the way to the edge of the universe. That is my explanation for a 6-year-old, but Ale knows how to talk to. Now, your daughter is only 4, right?
My daughter is 5.
5, all right, okay. So she'll soon start asking you these questions, Ale.
Yeah, she'll ask you this question.
Did you mention, Carlos, that there is no air in the space? I forgot if you mentioned that.
That there's no air? No, I said space is empty, right?
It's empty, but okay. But
like, if you're a 6-year-old, empty, like a cardboard box is empty. But it's not the same empty.
Anyway, right. So should we do the next question, Daniela?
Yeah, so who knew the most difficult question would come from a 6-year-old? So the last and final question is from, again, Vasu and Chennai, and they ask, what is the origin of our universe?
Okay, Carlton and Ale and Anna know the answer to that.
It was the second part of the question that you sent, which was is there a starting and ending point? And the ending point of the universe, I find a particularly interesting question, in that we know that the universe is expanding. So from that, we've got a number of scenarios. One is something we call the Big Rip. That is, if the universe keeps expanding forever, eventually matter gets pulled apart. There's just nothing anymore in any form that we know. And the other one is, of course, the heat death of the universe and the Big Freeze, which all sounds very scary. But eventually the stars will run out of their fuel, they'll stop burning, the black holes will evaporate, everything will cool down, and there's just not going to be much more to do in the universe.
That's quite a long way in the future, isn't it, Anna? So that's a few billion years away, yeah.
A very long time, yes.
Is there anything credible that can give you a big rip? You need some sort of phantom dark, like in cosmology language, you need W less than -1, right? You need the energy density of the dark energy to go up as the universe expands. Is that
well, if you just have accelerating expansion, it will happen, I think.
No. If it's a cosmological constant, nothing rips apart, because we call it accelerated, but in a sense it's not. It's tending to a constant. The Hubble constant tends to a constant value. So the thing that's accelerating is a particular galaxy, because as it gets further away, h times its distance goes up. So its velocity from us accelerates. But actually, something a megaparsec or something a million light years away, if if lambda CDM is correct, will always move away at the same speed. And so there's nothing gets ripped apart in that scenario. I think you need the Hubble rate to shoot up, which you get as soon as the dark energy density increases as the universe expands. But I don't know if that's like possible.
What about the other part of the question? So I don't know if somebody wants
the question,
to say,
right? The question was the beginning, no? The start of the universe.
How did the universe begin?
Yes.
I would say that's a very interesting philosophical question, but from a scientific point of view, we don't have any way to answer that question other than speculate, right? And that's because there is a physical limitation that we have at the moment, that basically there are clouds. Basically, we can see to the past of the universe just by seeing longer and longer distances. We can see how the universe looked like in the past, but actually it turns out that there's an edge for the universe, a visible edge for the universe, right? So there are clouds that basically don't let us see through the clouds, right? And that's the physical limitation. That's the reason we don't know how the universe started. And also another reason why there is such an edge is because
Well, there's another reason, right? That's a practical reason, but there's also a theoretical reason, namely that we have a wonderful set of theories in physics. One is the theory of general relativity by Einstein that explains how the universe expands and how the universe evolves. Then we have at the other end the theory of quantum mechanics that explains how atoms work and how elementary particles work. And to answer the question of how the universe began, you need to understand the two at the same time. You need to understand general relativity and how it interacts with quantum physics. And that is a theory that doesn't exist. It has a name, but it doesn't exist. It's called quantum gravity. It's a theory that defeated Einstein and more recently Stephen Hawking. The two of them spent large fractions of their life trying to develop a theory of quantum gravity, which is what's needed from a theoretical point of view to answer the question, how did the universe begin? But that theory doesn't exist. And until the theory exists, if ever, we just simply don't know the answer. There are things that us cosmologists don't know the answer to. Many questions, that's one of the main ones. How did the universe begin?
Brilliant. That was perfect. Thank you all so much.
This year's Royal Society Summer Science Exhibition goes online, a free celebration of science from across the UK, both past and present. From July the 13th to the 17th, you'll be able to enjoy a series of talks and discussions, live events and interactive digital exhibits, and there will be something for all ages to enjoy.